Hi. Today we will look at what is to me an interesting problem in probability theory. Let's start with a statement of the problem, and then we will solve it and explain the most important aspects of the problem along the way. The problem is relatively easy to state. We draw n numbers from the uniform distribution on the unit interval from 0 to 1, and we denote those values by x sub 1 to x sub n. This means that the values obtained will be from the unit interval and in a way that all values are equally possible. For the values we get, we pick the smallest and the largest value. We denote by x sub s the smallest of the values and with x sub l the largest of the values. After we know the smallest and the largest value of the sample, we take the difference between those two values and then we ask how is this new value distributed. To make it more clear, let's look at an example. Here we have a sample of three values, 0.3, 0.6 and 0.2. In this case, the smallest value is 0.2 and the largest one is 0.6. So the difference between them is 0.4. We want to know what can we expect when we repeat this experiment a number of times for any sample size. We know from the constraints of the problem that d lies somewhere between 0 and 1. But which values are more likely to be obtained? From the outset, we can see that ordering is going to be an important part of the problem, so let's start with the concept of order statistics. Let's say that we have a sample of size n same as before. This time, let's reorder the values to form y sub 1 to y sub n. We see that the y's have the same values as the original sample, but they are in increasing order. In our introductory example, we had x sub 1 be 0.3, x sub 2 0.6, and x sub 3 0.2. This would give us y sub 1 to be 0.2, y sub 2 to be 0.3, and finally y sub 3 to be 0.6. Once we have the values ordered, we can ask the question, how is the smallest value distributed? What about the second smallest, or the largest? We can pick any integer from 1 to n and sketch the probability density function for the corresponding y sub k variable to see how the values are distributed. The formula is somewhat tricky, but the most important parts are the cumulative function and the density function, which are given for our case when the initial variable has the uniform distribution. Remember, all of the samples are drawn uniformly from 0 to 1, and here we have the density and the cumulative function. The formula is general, but we are interested in two cases, the smallest value, y sub 1, and the largest value, y sub n. And the corresponding probability density functions are given here. Remember, we denoted the smallest value, x sub s, and the largest value with x sub l. Finally, we get to look at something. The graph shows us the probability density function for the smallest value of the sample in the case when the sample size is 10. The horizontal axis represents the range of values the smallest value can obtain. Since the range of the uniform distribution was 0 to 1, the smallest value can be any of them, but obviously they're not all equally probable. Intuition tells us that if you take 10 random numbers from 0 to 1 in a uniform way, it is more likely that the smallest value will be closer to 0 rather than to 1. And this graph shows us that. We see that the smaller values are more probable, as the probability density function shows. The interpretation of the graph is that if we are interested in the probability that the smallest value will be in some range, let's say from 0.1 to 0.2, then we need to calculate the integral of the probability density function from 0.1 to 0.2. This applies to all intervals, or if you want, measurable sets, but let's not get into that. In case anyone was wondering, this is the probability density function for the largest value of the sample. Again, in the case when n is equal to 10. Not only does it show that higher values are more likely, as we expected, but we can also see that the two graphs are mirror images of one another. This can be seen from their formula, but it also makes sense due to the nature of the problem, due to the symmetry of the smallest and largest value, and that the distribution is uniform. In the last two slides, we reminded ourselves what probability density functions stand for, but unfortunately, these results do not help us here, because we are interested in the relation between the smallest and the largest value, and not just in those values themselves separately. We need to see how they interact, and this is exactly what the joint probability density function does. Just as in the last slide, the probability density function showed which value, singular, is more likely, the joint probability density function will tell us which pair of values, for the smallest and largest value, are more likely. We have here the joint probability density function for the smallest and the largest values of the sample. X represents the argument for the smallest value, and Y represents the argument for the largest. And they're obviously from the unit interval, as we picked them from that set. And the condition that X is less or equal to Y is just a statement of the relationship between these two values. X represents the smallest value, so it will be lower. Having this function is a great step in solving the problem, but we cannot use it directly. From the joint probability function, we can get the individual probability density functions for X sub S and X sub L, the smallest and largest values. The probability density functions we saw in the previous slides. This gives us an idea to change the variables for the joint probability density function so that one of the arguments has the interpretation we want, the difference between the smallest and the largest value. Then we use this joint probability density function to get an individual density function. I know I just said a lot of things, but in the rest of the video we will go through all of those steps. And let's start with the change of variables. The choice for the first variable, let's call it u, is to take y minus x, as this represents what we want to get at the end. This is what we usually want to establish with the new variables. They should be relevant to the problem at hand. The other variable can be chosen in a number of ways, so long as the transformation is invertible. By invertible, I mean that we can get x and y in terms of u and v, and we can see that this is the case here. Now, we use the theorem from calculus that tells us how the new joint probability density function, labeled g, is expressed in terms of the old probability function. Applying the theorem gives us the density function we are looking for. Remember, n is the size of the sample we are looking at, the quantity of numbers we pick from the unit interval in just one experiment. The whole point of the change of variables was to have the information about the difference in one variable, which we did using the new variable u, and then to calculate the marginal probability of that one variable, which will yield the final result. We need to calculate the marginal probability density function for the variable u, so we integrate over all possible values of v for a given u. The upper limit is the consequence of the change of variables theorem, where we get that the new joint probability density function is non-zero on a triangle defined with 3 points, 0, 0, 1, 0, and 0, 1, as can be seen on the following image. This image shows the region defined by 3 vertices, 0, 0, 1, 0, and 0, 1. In this region, the new joint probability density function was defined, and outside of it, it is equal to 0. In other words, values outside the triangle are not possible. We needed to calculate the marginal probability for the variable u, which is on the horizontal axis. To do that, we needed to integrate over all possible values of v for that argument of u. So if we fix u here, then we need to integrate from 0 to this point, which is defined by v equals 1 minus u. All of that effort was made to get to this formula, which finally tells us how the difference between the largest and the smallest value is distributed. Let's see how it looks like for a given value of sample size. The graph shows us the density function for the difference in the case when the sample size is 10. So if we take 10 numbers from the unit interval, and then repeat that experiment a large number of times, we expect the difference to be in most cases between 0.8 and 0.9. At the end, let's take different sample sizes and see what is the expected difference. The sample size is in the first column, the second column represents the theoretical expected difference, and the third column shows us the experimental results, where I wrote a computer program which did the sampling, and for each sample size, the computer repeated the experiment 1000 times. Obviously, the value is getting closer and closer to 1, and we see the formula for the expectation. And that's it. Thank you for listening. I hope you found the problem interesting and that you learned something. Goodbye.